Welcome to ASU's University Academic Success Programs. This video will cover the topic, vectors and their applications. When we learn about vectors, we learn that there are vectors and scalars. A scalar is a number. It has magnitude, but that's it. A vector also has magnitude, or value, but it also has direction. A commonly used vector is speed and direction. For example, one could say, right now we are driving 55 miles per hour northeast. 55 is the magnitude of the speed, and northeast is the direction of travel. This is also called velocity, a vector of speed and direction.
So I suppose that's the basic form of a vector. How do I draw and write out the vectors?
Good question. Let's look at a coordinate plane. We'll mark the point 3, 2, and now we'll draw an arrow from the origin to this point. Now, to learn to write out vectors and their components, and note that here they will be rectangular components, we will first need to review the unit vectors I hat and j hat. I hat is the unit vector in the x direction, and j hat is the unit vector in the y direction. As we learn in class, a unit vector has a magnitude of 1. This vector ending at 3, 2 has an x component and a y component, which are based on the x value and y value of the ordered pair. Each component is written in terms of a unit vector, because a scalar multiplied by a vector increases its magnitude. What I mean is that the x value 3 multiplied by that unit vector I hat creates a vector with magnitude 3 on the x-axis. And the y value 2 multiplied by the unit vector j hat creates a vector with magnitude 2 on the y-axis. These are the x and y components of this vector, 3i hat and 2j hat. We write it like this: 3i hat plus 2j hat, or 3, 2 written in triangle brackets. And to give this vector a name, we name it with a variable with a half arrow on top of it. Let's call this vector v.
I understand now. So the vector is 3 units to the right in the x direction and 2 units up in the y direction. We have the magnitude of the components. How again do I find the magnitude of the whole vector?
To find the magnitude of v, we use this formula. The magnitude of v equals the square root of x squared plus y squared. And the x and y in the formula are the magnitudes of the x and y components, 3 and 2. If you think of the vector as a hypotenuse of a right triangle, and the components as the legs, this formula really is the Pythagorean theorem. How about you find the magnitude of v?
Okay, so I substitute 3 for x and 2 for y in the formula, written as square root of 3 squared plus 2 squared. This is square root 13, which cannot be simplified. Should I find the decimal form of this or leave it how it is?
Usually it is better to leave it in exact form, so you can leave it as it is. You are right though, the magnitude is square root of 13. So this is a vector 3i hat plus 2j hat with a magnitude of the square root of 13. We can use trigonometry with the components to figure out the angle between v and the horizontal. This now leads into our application of vector decomposition in a physics problem. Let's look at the classic inclined plane problem. Suppose we have an inclined plane with a given angle of incline theta, and an object of given mass m sliding down the plane. We are also told that there is no friction between the object and the ground. Let's draw a Freebody diagram for the object with all forces acting on it, and it will be beneficial if we have the surface of the plane be the x-axis, and then have the y-axis be normal to the plane. What forces are acting on this object?
It appears that there is the force of gravity and a normal force, right?
Yes, indeed. These forces we will draw are vectors. They have a magnitude and a specific direction. Gravity always points downward to the Earth's surface. If it pointed in any other way, well, let's just say we would be falling in strange directions. Now the normal force, which we usually see points opposite to gravity, is actually not this time. It points normal to the surface, which goes along our y-axis. Our force of gravity, with a magnitude of mg, we can see does not follow an axis. It is a vector that can be split into 2 components. We will use trigonometry to figure out the x and y components. Using similar triangles, we can see that the angle between the vector and the y-axis is the same as the angle of incline theta. We will start by finding the x component, which we will draw on the bottom so that we can see the right triangle, and the y component will be along the y-axis. So we know the angle is theta and the hypotenuse is mg. How can we find the x component?
We can use the sine function sine theta equals to fgx over mg. We multiply both sides by mg to find that fgx equals to mg sine theta.
Exactly. And assuming that left is negative, this is in the negative x direction. So our component with the unit vector is negative mg sine theta I hat. Now let's find the y component.
We can use cosine this time. Cos theta equals to fgy over mg. We multiply both sides by mg to find that fgy equals to mg cos theta.
Right again, and this is in the negative y direction. So we write the component as negative mg cosine of theta j hat. Now that we have these components, we can write out force net equations in the x and y directions. In these equations, we would eventually find that the normal force is actually equal to the y component of the gravity vector. This means that the normal force in this problem is actually less than the weight of the object. If the object were placed on a scale on the inclined plane, it would actually give a weight that is less than the object's actual weight.
Okay, so what I am understanding here is that our gravity force vector can either be written by its magnitude or as negative mg sine theta I hat plus negative mg cos theta j hat.
Yes, exactly.
So if we are given a vector with magnitude, if we set that into a coordinate system, we can use trigonometry to break that vector into components. Doing so is useful in free body diagrams when force vectors are not horizontal or vertical. This is because their components are horizontal and vertical, which can then be used in net force equations.
Great understanding. It looks like you're ready to apply vectors in physics problems.